Hello, my name is Alani Martinez, and in this video we will be solving the problem below. The problem is about boundary conditions on D and E at the interface between a dielectric and free space. The problem below states, for x is greater than 0 is free space, and for x is less than 0 is a dielectric with dielectric constant equal to 5. On the surface of the dielectric at x equals 0 is a sheet charge density of 2 coulombs per meter squared. If d sub a is equal to 4a sub x plus 5a sub y minus 10a sub z coulombs per meter squared for x is less than 0, find the electric flux density for x is greater than 0. So the idea is we know d on the left side, the dielectric, and we have to find d on the right side, the free space, using boundary conditions. As shown below, we first have to start by drawing the interface at x equals 0. The left side is region A, which is x is less than 0, and epsilon sub Ra equal to 5. The right side is region B, x is greater than 0, and it's free space, so epsilon sub Rb equal to 1. The normal to the surface is along the positive x-axis from A to B. That's important because the boundary condition for the normal component of D uses that direction. Right on the surface at x equals 0, there's a cheat charge equaling to 2 coulombs per meter squared. That means we cannot say D is the same on both sides. We have to add the cheat charge. To go from D on one side of a boundary to D on the other side, we use electromagnetic boundary conditions. There are two conditions. Tangential E is continuous, so E sub AT is equal to E sub BT. Normal D jumps by the surface charge, so D sub B minus D sub A is equal to the surface charge. We will use the tangential one to get the y and z components of D on the B side and the normal one to get the x component on the B side. First, I'll do the tangential components. From Maxwell's equations, for a surface with no surface electric field source, the tangential components of E must be the same on both sides. Therefore, E sub AT is equal to E sub BT. Tangential here means directions along the surface. So that's the y and z directions because the surface is on the plane at x equals 0. The problem gives us D not E. We know that D is equal to epsilon times E, so E sub A is equal to D sub A over epsilon sub A, and E sub B is equal to D sub B over epsilon sub B. In region A, the dielectric is equal to 5 epsilon 0, and in region B, free space is equal to epsilon 0. Let's do the y component first. For the y component, the tangential condition says that E sub AY is equal to E sub BY. Replace E with D over epsilon, and that gives us D sub AY over epsilon A is equal to D sub BY over epsilon B. Plug in epsilon A, which is equaling to 5 epsilon 0, and epsilon B, which is equal to epsilon 0, and that will give us D sub AY over 5 epsilon 0 is equal to D sub BY over epsilon 0. Here, the epsilon 0's cancel, so we get D sub AY over 5 equaling to D sub BY. Now we just plug the number for D sub AY from the given dA of the problem, and that gives us that the y component is 5 coulombs per meter squared. So plugging that in, that would give us that D sub BY is equal to 5 over 5, which gives us the y component of D on the B side, which equals 1 coulombs per meter squared in the y direction. Now we do the exact same thing for the z direction because z is also tangential to the surface. So we start from D sub AZ over epsilon A is equal to D sub BZ over epsilon B. And now doing the same thing as before, we know that D sub AZ over 5 is equal to D sub BZ. From the given dA of the problem, the z component is negative 10 coulombs per meter squared. So that gives us that D sub BZ is equal to negative 10 over 5, which equals negative 2 coulombs per meter squared in the z direction. Now we find the x component. For the normal component of D, we do the Gaussian pillbox that straddles the surface. The boundary condition for D normal is D sub Bn minus D sub An is equal to the cheat charge, where n is in the direction of the surface normal, which in this case is in the positive x direction from A to B. So we write D sub Bx minus D sub Ax is equal to the cheat charge. We already know d sub ax from the given problem, and that is 4 coulombs per meter squared. In the cheat charge, we also know that it's 2 coulombs per meter squared, so that gives us that d sub bx minus 4 is equal to 2, and therefore d sub bx equals 4 plus 2, which equals 6 coulombs per meter squared in the x direction. Sometimes a common mistake is that people forget the cheat charge and write d sub bx is automatically equal to d sub ax. But here we had a cheat charge of 2 coulombs per meter squared, so we had to add it. Now we have all three components on the free space side. Dx equals greater than 0. We know that d sub b is equal to 6a sub x plus 1a sub y minus 2a sub z coulombs per meter squared. That is the electric flux density in region B. A little short recap. So the steps were: identify the two regions and their permittivities, use tangential E to get y and z, divide the A components by 5, use normal D with the cheat charge to get x, add cheat charge to the ax component, put the vector together in the final answer as stated before, giving us d sub b equaling to 6a sub x plus a sub y minus 2a sub z coulombs per meter squared. And that's it.